So yeah, I am excited to be talking about these BE2 measurements in light radioactive nuclei that we have been performing at the University of Notre Dame. And as mentioned, these are primarily have been for guiding ab initio calculations. Okay, so the first thing that I want to address as sort of always the basic fundamental question of really any science that's done is, well, why are we doing this? What's the goal here? And in our case, and the group at Notre Dame, and for myself especially, we're interested in the structure of nuclei. And I think that's probably a common thing for many of the people here. And we know that nuclear structure isn't necessarily a simple thing, that depending on what area of the chart of nuclide you are on, you can see different shapes emerge, you can see different collective structures. And one area that I'm particularly interested in is this area in light nuclear physics, where we see these two interesting structures. As examples, we see cluster structures emerge, and we see halo nuclei. So cluster structures have been seen in beryllium-8, they've been seen in carbon-12. A famous example in carbon-12 is the Hoyle state, where you have your carbon-12 nucleus, and in an excited state, it subdivides into three loosely bound alpha particles within the carbon-12 nucleus. So that's an example of an interesting or unusual structure that emerges in the light area of the nuclear chart. Halonuclei is another example where you have a central core of nucleons, and then surrounding it at a much farther radius, you have either neutrons or maybe even protons orbiting around the central nucleus. And these are unusual structures, and we don't understand what causes them to occur. We don't fully understand what causes these structures, and we really would like a theory that can start from the basics of what we know about the nuclear interaction, and can both explain these structures and hopefully be able to predict when they will occur. Now that's sort of a tall order right now, but that's what we want to move towards. So to orient ourselves where we are, I have here a chart of the nuclides, and I've boxed in red some examples of these nuclei that have these unusual structures. So as I've already mentioned, carbon-12, beryllium-8, both have seen examples of clustering. Lithium-7 is also another prime candidate for having clustering going on. And then helium-6, beryllium-11, lithium-11, all have been seen to have halonuclei structures. Now, that's not to say that I've boxed the only nuclei that have these structures. There are many others that are currently under investigation or that have been shown to have these sorts of structures. What I want to show is that this is sort of the area that we're working in. This light area of nuclear physics is the area that we're going to be investigating. Now, I've already said we want a sort of a fundamental theory or fundamental approach, and I'm talking about areas in light nuclear physics. You can almost see it coming that the theory that we're going to want to work with here is these Abenitio theories, these Abenitio calculations that have made so much progress in this region of the chart of nuclides. So this is an experimental talk. I don't want to spend too much time talking about the Abenitio theory, but I do want to explain a little bit about it as it's an important motivation for why we did these measurements. So the idea behind Abenitio theory is you want to start with first principles. So you're starting with the nucleon to nucleon interactions, maybe even three-body nucleon, nucleon, and nucleon interactions. You're using those to build up an interaction for your nucleus. You put that into your Schrodinger equation, and from that you can solve the Schrodinger equation to get out whatever values you're interested in. Right. Well, that's the ideal. That's the idea. But as it turns out, reality is pretty complex. Describing the interaction is quite difficult. As I think most of us know, the interaction between nucleons comes from the quarks and gluons inside the nucleus. The resultant force it's a resultant force. And as of right now, it can't be described without having to normalize or make comparisons to experiments. So that adds an additional layer of difficulty into creating these interactions. Solving the Schrodinger equation directly also is impractical. that, or is at least difficult. There are, as you increase the number of nucleons, your wave function becomes increasingly large to deal with, and you have to have some way of truncating that wave function, truncating that basis. And there have been multiple approaches to tackle this. I'm going to talk a little bit about the no-core shell model approach. My group has been very blessed to have had a group at Notre Dame who works in these no-core shell model approaches. So we've been able to work very closely with them. And I want to explain just a little bit about these calculations so that later on, when we're making comparisons to them, everyone has the background to understand what's going on. So again, with these calculations, the goal is to start from the basic nucleon interactions and then to describe your wave function to a certain level. And the way this is done in these calculations, so it's a no core, which means that all the nucleons are included. There isn't any sort of inert core that's inert core. You treat all the nucleons as interacting. And it's also shell model. So you're putting nucleons into a shell model like picture. And the way that you kind of increase your, you make your wave functions more complicated by increasing and adding in more and more basis states is you have this parameter called inmax, which dictates the total number of excitations allowed in this shell model like picture. So inmax equals 2, you're allowed 2 total excitations, and that puts a limit on the number of basis states allowed. And so as you perform these calculations, typically they are increased in max, and as that increases, your total wave function gets larger, and you end up dealing with more and more configurations as you go on to solve this in a matrix. So the inmax is increased and that's performed for different calculations. Something else that's varied is the energy scale, which is shown here by h bar omega, and that affects the shallowness or deepness of this potential well that the nucleons are placed in. And practically speaking, that also changes the shape of the wave functions used. And so that's another parameter that's varied to see what, to try to match the natural length scale of the nucleus. Okay, well, what does this practically look like? So the idea in this approach is to turn the quantum mechanical many-body problem into a linear algebra problem, where you can then just diagonalize a matrix and get out eigenvalues for whatever parameter, whatever observable you're looking for. What you can see in this graph on the left is that as inmax increases, the total dimension of this matrix also increases. So I'll be talking more at length about beryllium 7 and lithium 8 later. And what we can see is as we approach this 10 to the 10 dimension, that's the current limits of what the calculations can handle, at least for the group at Notre Dame. So what that means is for lithium 8, for example, we can't really go past inmax 14. Beryllium 7 going past inmax 16 would be hard. And that puts a hard limit on how complicated these calculations can get, how you're limited by the inmax. So typically for these calculations, we'll see graphs such as this. This is a calculation done of the ground state energy of helium-4. Each of these lines with the numbers next to them is a different inmax value. So inmax 6, 8, 10, 12, 14, and 16. And they're performed for a variety of these h bar omega shown on the x-axis. And what you hope to see from these calculations is as you increase the inmax, adding in more and more of these wave functions or these basis states doesn't really do you any more. You're converging towards a value. So the other thing that is seen is the h bar omega matters less and less as you go to higher inmax. So when you have these sort of flat lines, that's a telltale sign that you have a converged result. And that you can just pull a value from that and compare it to experiment. Okay, so that's enough of the details of the no-core shell model, and this is only one of the many approaches used. I can't talk in detail about all of them, but the idea is that they are all follow sort of fundamental approaches, that they all start from first principles. However, different types of calculations, different Abenitio approaches oftentimes still yield divergent results despite attempting to start from first principles. So this is an example where we see calculations performed in nitrogen 14. These are BM1 transitions, and there are comparisons of no-core shell model on the left column versus IMSRG calculations, another kind of ab initio calculation. And you can see that depending on the type of calculation, the results can vary, even up to like factors of 2 or 4. So as an experimentalist, this is obviously, this adds a layer of confusion because, well, these are both first principle. Why are they getting different results? How would you find a way to decide to trust which one? Additionally, the choice of interaction can cause differences as well. So I have here data or calculations performed using Green's function Monte Carlo calculations in Beryllium 10. And each column shows a different interaction used. And for these BE2 calculations, you can see changes up to a factor of 10 depending on the choice of interaction. Now, as an experimentalist, the way that I can get a grasp on how these calculations are doing are to compare them to an experiment. So if one calculation I compare to experiment and it verifies that, that gets me a better sense that the calculation is doing well. So there is, because of these differences, because there are differences in these ab initio calculations due to choices of calculation, due to the choice of interaction, there is a need for experimental measurements to benchmark these calculations. And so that is what I decided to do for my thesis work. And I chose to do this by measuring additional BE2 values. The BE2 is a good candidate to benchmark these calculations for a variety of reasons. BE2 is a reduced electric quadrupole transition probability. The BE2 is a sensitive value to calculation choices. As already shown, it can distinguish between different interactions in certain cases, and we have seen it to be sensitive to differences in these calculations. The theory of electromagnetic transitions is well understood. So from an experimental standpoint, it'd be very nice if we can measure something that we don't have to fall back on a nuclear model to understand. And electromagnetic transitions are fairly well understood. And also the BE2 connects to nuclear shapes. Because it's connected to the electric quadrupole moment of the nucleus, that is related to how charge is distributed across the nucleus. And so by measuring BE2 values, we're getting us back to what we're interested in, which are these nuclear shapes. So it makes sense that we're measuring a value that connects to nuclear shapes, that's eventually the sort of parameter we want these ab initio calculations to be able to predict for us. Okay, so we know the thing we want to measure now, but the question is, where do we measure it? Well, all of these values shown in black on this chart of the nuclides are stable values. And pretty much all of the stable nuclei have had their BE2s measured and measured very well. These measurements have been done since really the 60s and 70s even. Pardon. So if we want to make additional measurements to help provide more checks, more benchmarks to these calculations, we're probably going to have to move to measurements in radioactive nuclei. We also are interested in measuring nuclei that might have these interesting structures in them. And so we're going to measure sort of around these red boxes. So beryllium 8, maybe even lithium 7 are known to see some clustered-like behaviors. So we decided to measure beryllium 7 as one example. Another measurement we'll make later is in lithium 8, which is also close to these nuclei that are known to have collective structures. So these were the 2 nuclei we chose to measure in this program. They are light nuclei with potential cluster structures. And you can see oftentimes lithium 7 is described as a triton in an alpha particle loosely bound in a nucleus. Beryllium 7 can be fairly easily described as a helium 3 in an alpha particle bound together. And then lithium 8, maybe it looks like a lithium 7 with an additional neutron, or maybe adding in the neutron destroys what cluster structures are there. We don't know, but making these measurements, we already have sort of a direction, a suspicion that they might have cluster natures or these interesting structures there. So they're good candidates for measurements. Okay, now I want to talk a little bit about how we're going to measure these BE2 values. So we use the old, but the reliable technique of Coulomb excitation. The goal is to excite our target nucleus with an electromagnetic interaction. So in the schematic, we have a beryllium-7 nucleus that is sent fairly close to a gold nucleus. Gold has a high Z number, so it has a high electric field that comes off of it. And there's some probability that the gold will emit a virtual gamma ray and excite the beryllium-7 nucleus. So in this schematic over here in this level diagram, this would be an E2 excitation up to an excited state, and then the beryllium-7 will de-excite by emitting a gamma ray. The goal of this is to keep the beryllium-7 far enough away from the gold that we don't go past the Coulomb barrier, that we stay in the safe Coulomb region, which means that the short-range nuclear force isn't going to interact with our particle. And that means that any excitation that happens in this beryllium-7 nucleus should be due to the electric component. All right, so here is the actual level diagram of beryllium-7. We can see that it is a mixed transition from the 1/2 minus to 3/2 minus, which means that the gamma ray that comes out will be a mixture of magnetic dipole, electric quadrupole radiation. However, because we're exciting up via the electric field, all of the excitation up is going to be this E2 transition, which means that by measuring the gamma rays that come out, we can measure the BE2 up and determine what the inelastic cross-section, what the cross-section is for this excitation. And if we can measure this cross-section, that relates directly to the BE2 value with some other parameters that we can calculate from the experiment. This is a very similar situation for lithium-8. So their mixed transition. I will also point out that these light nuclei only have one bound excited state before in beryllium-7 you get to the alpha helium-3 breakup, and in lithium-8 you get to the neutron emission threshold. So what that means is that when we perform these measurements, we're expecting to see a more sparse spectra because there's only going to be the one gamma ray we should see, only the one gamma ray from this one bound excited state. Pardon. Okay, so these experiments were all performed at the Notre Dame Nuclear Science Laboratory. I want to talk just a little bit about the lab for those who are not familiar. The majority of the work done at the NSL is done with one of these three accelerators. The accelerator seen on the left in this image is the 10 megavolt tandem Van de Graaff accelerator. It is used primarily for nuclear structure experiments like this one, and also some nuclear astrophysics experiments. This image is the 5U, the 5 megavolt accelerator being lifted by a crane down into the tower where it currently sits today. This accelerator goes up to 5 megavolts and runs with much higher intensity beams than the FN can usually achieve, and has been largely used for lower energy, lower cross-section, or lower yield nuclear astrophysics measurements. Seeing this final picture here is the 3 megavolt 9S accelerator is seen in the background. This accelerator has been used very widely for application studies. So a lot of PIXI and PIGGY is done for identifying isotopes materials. It's also being used in coordination with the radiation laboratory at Notre Dame to study radiation damage for materials science standpoint. And this photo is a lab photo. This photo was taken 3 or 4 years back. So not everyone in this photo still is at the University of Notre Dame. Many of these grad students have graduated, but it does give you a sense for the size of our lab. So that's the lab in general. And we use the FN tandem Van de Graaff accelerator seen here to produce a beam of lithium-6 at 34 megavolts, or 34 MeV rather. This beam is then sent following this red path to one of the permanent experimental installations, which called TwinSol. TwinSol is how we produce radioactive beams at Notre Dame. So TwinSol, as the name might suggest, is composed of 2 large superconducting solenoid magnets. They are capable of going up to about 6 Tesla each. And the question, of course, then is, well, how do these magnets help us produce a radioactive beam? Well, the way that we produce this radioactive beam is directly before TwinSol, there is a production target, normally filled with some sort of gas or with a foil on the gas cell. In the case of this experiment, the gas cell was filled with deuterium. And we bombarded this deuterium with our lithium-6, and a whole host of reactions occurs. We can have proton donation to the lithium-6 to make beryllium-7, or neutron donation to make lithium-7. We can also just have elastic scattering off of the gas in the lithium-6, and we can make helium pretty easily. So we end up creating a cocktail beam that scatters out of this gas cell and enters into twin sol. Now, the large solenoid magnets of twin sol then bend the particles that come out based on their velocity, their mass, and their charge. So each component of this cocktail beam will be bent at a different radius or to a different focus. And by tuning the magnetic field, we can then tune and focus our desired beam of beryllium-7 to a central point at the middle between the two solenoids called the crossover point. A collimator is placed here such that we focus the beryllium-7 through the collimator, and the other parts of the beam are either under or over focused and will be separated out by this collimator. So that's how we produced our radioactive beam of beryllium-7. We had a beam of 10 to the 5th particles per second of beryllium-7, and we ran for 3.5 days in this experiment. Just as sort of another note, the beam energy of this beryllium-7 was at 30.4 MeV, which is well below the Coulomb barrier of 39.3 here. So again, we're trying to stay in that safe region. We don't want nuclear components of to our excitation. We then sent this beryllium-7 beam to a detector to do particle identification. The beam was identified as being 85% beryllium-7, seeing this large peak here, and the other contaminants are labeled. They're at much lower energy, so we can separate them out in our spectrum. Okay, so this beam of beryllium-7 is then sent to our detectors. We have here our gold target, which our beam hits and scatters off of. It scatters into a silicon detector placed directly after the gold foil. And there's some chance that when the beryllium-7 hits the gold, it's excited during the scattering and emits a gamma ray. And directly outside of the chamber, there are 6 high purity germanium clover detectors from the Clover Share collaboration that were placed around the chamber. So in this experiment, we were measuring particle gamma coincidence. We were tagging out a particle and then looking for a gamma ray to cut down the, to make sure that our gamma ray seen was in coincidence with one of these particles. So these are some pictures of the setup. You can see here the gold foil as described earlier, and then the silicon detector directly afterwards. The silicon detector is segmented. It has 24 rings and 8 sectors. I'll show you what that looks like on the next slide. And then this chamber is closed up. You can see right here, directly around it, there are 6 these high purity germanium detectors that are placed directly up against it to measure the gamma rays. The silicon detector, as I mentioned, is segmented. It's segmented into concentric rings, which give us a theta angle to our scattering. And on the back, it's cut into almost pizza slices to give us a phi angle. So we have a theta and a phi for our scattering, and that gives us geometric information on where our particle hits. And that will become important in the analysis later. So we ran this experiment for 3.5 days, and we placed some gates on particles to look at the gamma spectrum. And our final what the final gamma spectrum looks like is shown this figure on the left. Now, the first thing you will probably notice is that this is a very sparse spectrum. A combination of having a low beam rate due to our radioactive beam and also requiring particle gamma coincidence means the total number of gammas seen in a final spectrum is quite low. However, we do see with very good resolution several gamma lines here. These are all gamma rays that came from gold Coulomb excitation. So in just the same way as we're using our gold nucleus to excite our beryllium-7, our beryllium-7 nucleus can excite our gold. And we see in this gamma ray spectrum, there's a 547 line, 279, a 77, all those corresponding with transitions in the strong gold transitions. And we also see a 67 keV line that was identified to be X-rays from gold. And this gave us, this is great because we can see our energy calibration is working very well. We know we're doing Coulomb because we see these lines coming out. But we don't see our beryllium-7 peak. And this was at first initially confusing until we remembered that our beryllium-7 is emitting gamma rays in flight. So all of the gamma rays emitted are going to be Doppler shifted. We would need to do a Doppler correction. So in the process of this analysis, I did perform a Doppler correction, and we see our final peak positioned here. This peak is our beryllium-7 Be2 peak, and it is at the energy we expect. It's at 430 keV, so we know this is the correct gamma ray. And we have a final peak with 30 counts plus or minus 6. Okay, so we have the counts from our experiment. We have the number of gamma rays we saw. We now need to use that to get to a cross-section. Well, we have to account for detector efficiencies. That was fairly straightforward to do by putting a gamma source with a known activity into our chamber. We then also had to account for our beam rate. And measuring the beam rate for a radioactive beam isn't entirely straightforward. You can't just put a Faraday cup in front of your beam because it's such a low count rate, it won't be picked up by most those Faraday cups. So what we decided to do instead, we already see elastic scattering from our beam into our silicon detector. We decided to look at Rutherford scattering into our detector and use that to figure out our beam rate. Well, this was a great idea, but as it turns out, the beam that comes from twin cell is not a point-like beam. It is, in fact, somewhat broad and it was a little bit offset, which meant that our scattering plots, our elastic particles seen in the rings, did not follow a Rutherford distribution. So I used a Geant4 simulation. I put all the geometries for our experiment into the simulation and altered the width and the position of the beam until I was able to replicate the shape of this experimental beam that we saw. So the experimental data is shown in this graph in red. The Geant4 simulation is shown in black. And we had really a range of values that were able to reproduce this beam. So this did add to the total uncertainty of the experiment. It added about 7% uncertainty. But we were able to then recapture our beam rates and use that to find our cross-section. So we were able to calculate a BE2. The BE2 3½ minus to 1½ minus in this beryllium-7 nucleus was found to be 26 plus or minus 6 from statistical uncertainties and plus or minus 3 from systematic uncertainties, e squared from e to the 4th. There were a couple of systematic uncertainties that we were not able to fully account for in this experiment. If someone wishes to ask me about those, I can go into more detail, but for the sake of time, I'm going to, for right now, just sort of leave those be. But we were able to measure this BE2, which this is the first measurement of this value. We now want to compare to Abenitio calculations. So what I have here is a plot of a variety of Abenitio calculations. The blue squares are Green's function Monte Carlo calculations done with 2 different interaction types. This red circle is a no-core shell model calculation, and this green triangle is a no-core shell model with continuum, formerly known as no-core shell model / renormalization group method. The idea of this calculation is you do a no-core shell model calculation and you explicitly add in you add in scattering states that are very hard to get to using a normal no-core shell model to try to encapsulate those sorts of states as well. Okay, so this is the comparison, our experimental value shown in black here with 1 standard deviation uncertainties. And there's a good bit of scatter in these theoretical points, but they do all agree with our measurement. They all do reproduce the experimental measurement. So that's exciting. There were additional no-core shell model calculations we would like to compare to, because it would be nice to know how different interactions affect the no-core shell model calculations. The problem that we ran into there was that these no-core shell model calculations that were being performed by our collaborators at Notre Dame were not converged. And I'm going to go back to our earlier discussion to talk a little bit about this convergence problem. So this calculation is the ground state energy of beryllium-7. And you can see as the dimension increases, as the Nmax increases, the values converge to the same point and they level off. which means that these are converged values, that they can be read off the graph or pulled from the calculations and be used with some confidence in the results. This is a Be2 calculation in Beryllium 7. And you can see that the H bar omega dependence is still there, even at the highest and max. And as you go increase in dimension, there isn't any sort of tapering off in these calculations. They just keep wanting to go up, which means it's basically impossible to know when these calculations will stop. Certainly at the highest and max that can be calculated, they haven't converged yet. So this was a problem. This was very disappointing initially, but our theory collaborators came up with a solution that helped to help this convergence problem. So instead of just plotting the Be2 of beryllium 7, they plotted a ratio of the beryllium 7 Be2 with the lithium 7 Be2. So this is a ratio of Be2 values in mirror nuclei. And you can see right away that these calculations are much better converged, and they converge very quickly, even by n max of 6. Pardon. And the lithium 7 Be2 is already known. That measurement has been made many times in the past. So we can easily create an experimental ratio to compare to. So that's what we did. We then compared to these ratios to get a better sense of how all these no-core shell model calculations were doing. And in the process, we found out another interesting element of this comparison, that the interaction dependence dropped out in this ratio comparison. So we see these first 4 points in this graph are no-core shell model calculations performed with different interactions, and they are all within 2% of each other. So they are all in very good agreement with each other. And that sort of interaction and dependence is exciting because it makes it easier to compare a no-core shell model calculation to a Green's function Monte Carlo calculation without having to worry about, are they using the same sort of interaction? There was a little more spread in the overall Abenitio calculations, but they did all agree with the experimental ratio and reproduce the value quite well. Okay, so just some takeaways from this beryllium 7 experiment. The very first measurement of this beryllium 7 Be2 was made. The Abenitio calculations are in very good agreement with the experiment, especially for the ratios. And now we discovered this this ratio comparison, which seemed to work a little bit better to grant faster convergence than just a Be2 measurement. We're now interested to see if this sort of comparison can be extended to other nuclei. Does this help these convergence problems in other nuclei as well? Is it something specific to beryllium 7 and lithium 7? As of this experiment, we didn't know, but we were excited to find out more. So at that point, we moved on to lithium 8. If you'll just give me a second to take a drink of water. Okay, so we have already measured the beryllium 7 Be2 value, now shown here in pink. And as already mentioned, the next nuclei we want to look at was lithium 8. So lithium 8 looks a lot like, does it look like lithium 7 with an additional neutron, or does it collapse down? We're not sure. We're excited to try and find out. So this was also performed at the University of Notre Dame. We produced a primary beam of lithium 7 at 26 MeV. Using this time a lithium 7 on a beryllium 9 foil, we were able to produce our lithium 8 and then use twin cell to separate out the lithium 8 of interest. The experiment produced 4 times 10 to the 5th particles per second, and we ran over the course of 5 days. The lithium 8 secondary beam energy was at 23 MeV, which is below the Coulomb barrier of 36 MeV. We had to run a little bit lower in energy because lithium on gold has a lower Coulomb barrier than does beryllium on gold. For this experiment, instead of using the high purity germanium detectors from Clovershare, we were able to use the lanthanum bromide detectors from the Haggard array. Kate Jones was good enough to let us borrow these detectors. They have been used at Notre Dame quite a bit, primarily for nuclear astrophysics experiments, but we were able to use these lanthanum bromide detectors for this measurement. And one thing that I was very excited about for using these detectors is that the overall efficiency of this array is much higher than that of the Clovershare array. And as we already saw, low statistics was one downside of the previous experiment. So this way we're increasing our overall gamma efficiency. We also invested in a new silicon detector with tighter rings that would enable us to do a little bit better of a job determining where our particle hits for our Doppler correction. Another point of note is that in the previous experiment, a lot of the equipment we used was borrowed from other places and had to be returned. And now that our first experiment had worked, we wanted to start developing our own equipment so we could be able to perform multiple of these measurements at Notre Dame. So I ended up designing quite a bit of the equipment for this experiment. So I had to work with a scattering chamber, developing the feed-throughs to go into it. I ended up building these detector mounts to hold the silicon detector and collimators. I had to work with the mounts we already had for the lanthanum bromide detectors, find ways of securely mounting them to get them as close as possible to the chamber. And because of this, we now have much greater capability of running these experiments at Notre Dame whenever we can get the gamma detectors to do so. So that's something that was very exciting for the continuation of these measurements. Anyway, this experimental setup is very similar to the previous experiment. We are doing particle gamma coincidence. We are sending our beam onto our gold target, scattering into the silicon detector, and this time measuring the gamma rays with the lanthanum bromides positioned outside of the chamber. So we did this. We ran for 5 days. And here is an example of a summed lithium-8 spectrum cleaned up over the course of the experiment. One thing that we did notice right away is that the absolute gamma efficiency was indeed higher for this experiment. However, the lanthanum bromides also bring in additional background counts. One challenge that these lanthanum bromide detectors bring with them is that they have internal radioactivity. So there is radiation that is emitted, just natural radiation present in these detectors. And you can see that some number of these radioactive decays did bleed in through our particle gamma coincidence. This little peak here at 1,500,000 or 150,000 channels is an example of an internal radioactivity peak. However, we are able to use the very good timing resolution of the lanthanum bromide and silicon detectors to cut out a lot more of this background. And we're then able to find a final peak of 43 plus or minus 14 counts, seen here in this figure on the left. This peak is positioned at 983 plus or minus 3 keV, which is within uncertainty of the fit of this 980 keV line that we know is the excitation line in lithium-8. So as the same with last time, we were able to fit this peak, get counts. We had to use a Geant4 simulation again to reproduce our beam rate, and we're then able to calculate a cross-section. So this is our B2 calculated from that cross-section. We have a value of 1.7 plus or minus 5 e squared for me to the fourth. We are still currently working on the systematics for this experiment. So there might be some systematic uncertainty added in later. And this experiment is not the first ever measurement of this BE2. There was a previous measurement done at Notre Dame using just particle detectors. And that experiment measured a value of 55 plus or minus 15 e squared for me to the fourth, which is very discrepant with our value. However, this older value, because it just used particle detectors, didn't have any good way of separating out lithium-8 excited in the reaction back at the production cell before it goes into twin cell, and with lithium-8 that scatters off the gold foil. And we think that's a reasonable explanation for why their value is so much higher than ours. So our experiment with more modern techniques, we are confident in our value. We then wanted to compare this value to Abenitio calculations. So shown here is our result with 1 sigma standard deviation. And we have here a no-core shell model calculation, a Green's function Monte Carlo calculation, and the single particle estimate for this nucleon. And what we see right away is that the agreement isn't quite as good, and the points are exhibiting more scatter than previously. So again, this is just one sigma error bar that's being plotted. We can't say anything definitive from this, but initially we're a little surprised that the results have more scatter than the Beryllium 7. But we want to move on to look at ratios. Because boron 8, which is the mirror nucleus of lithium 8, does not have a BE2 that's been measured, and because it's unbound to its first excited state. So I couldn't go and measure the gamma ray even if I wanted to. We had to use a different ratio for this experiment. We looked at the ratio of this Be2 to the electric quadrupole moment of the ground state of lithium-8. The electric quadrupole moment is akin to a ground state to ground state transition. And the same ratio was looked at by our theorist friends at Notre Dame for beryllium-7 and lithium-7, and they showed the same convergence behavior and the same interaction independence that we've seen in the previous Be2 ratios. So it's a different ratio. We're just using the available data to sort of help these calculations. Now, if we look in this comparison, we have the experimental ratio shown here in black, and we see that one of the no-core shell model calculations, the one with the de Géon potential, is doing a pretty good job of reproducing our result. However, the GIST16 and the LINPIC don't align nearly as well. There is about a factor of 2 difference in these calculations. This is the previous no-core shell model calculation, now shown with the ratio. I would have also have liked to have shown the Green's function Monte Carlo ratio, but we didn't have a ground state electric quadrupole moment for that calculation, so we couldn't make the ratio. But what we see is that while the ratios are a little more successful in agreeing with the value, that there is a good bit more spread in these calculations. And further, if we look at the convergence behavior of these calculations, it's not as well defined as we had previously seen. So by the time we get to the highest in max, this red line here showing the calculation, the lithium-8 ratio with the de Géon potential is converged, but for this GIST16 potential interaction, there's a factor of 2 difference depending on what h bar omega, what energy scale is used. And in this LINPIC interaction, the value starts going down, hits about halfway, and then starts going up again, which is called a bounce. It makes it very hard to predict where the final value will end up. So now we're actually not seeing as good convergence behavior from these ratios either. Now, our theorists, friends, are able to look into their calculations to try to find explanation to see why is this behavior so different for lithium-8 compared to beryllium-7, lithium-7. And one explanation that we found is that lithium-8 is an odd-odd nucleus, and that there are multiple ways to create a J in this nucleus. So because it's an odd-odd, there's a free proton and a free neutron that can either pair to create S equals 1 or pair to create S equals 0. And this adds with the L of a state to create the final J. So in the ground state, which is J equals 2 plus, the theorists looked at the calculations and saw that it is predominantly L equals 1, S equals 1 adding together to make a 2 plus ground state. However, the calculations were predicting about a 50-50 mixture for the first excited state being L equals 1, S equals 1 adding to a 1 plus J, and L equals 1, S equals 0 adding to a 1 plus. Okay, well, why does that matter? Why would that affect the Be2 value? Well, the Be2 the E2 transition can only affect the L of the nucleus. It can't affect the S of the nucleus. So there isn't any way of coupling this L equals 1, S equals 0 state to the L equals 1, S equals 1 state. And that means that the amount of this L equals 1, S equals 0 state is going to directly impact the final Be2 value these calculations give. So this calculation is very sensitive to this LS mixture. And this is something that the different interactions might handle differently. There is some initial indication that this mixing in the 1 plus state is coming from 2-state or even multi-state mixing, where there are higher 1 plus states that are mixing and merging with this first excited state. We're still sort of looking into this with the theorists. But this would, we would expect this to reduce the Be2 value. So sort of pulling some conclusions off of this lithium-8 experiment, the ratio still did improve the convergence, but we saw lithium-8 had interaction dependence where beryllium-7, lithium-7 did not. The lithium-8 also seems much more sensitive to the LS treatment of the interaction, while the lithium-7 and beryllium-7 appear much more indifferent. We also compared to other nuclei in the surrounding region that already had Be2 measurements. And this same LS dependence was also seen in one of the E2 transitions in beryllium-9. In that case, there wasn't actually nearby states for two-state mixing. So we're still sort of looking into why that's happening. But we're seeing some initial indications that LS mixing, that this can be an important value that impacts how these calculations work. And of course, this heavily mixed 1+ state does make for a very challenging calculation for these ab initio calculations. And I would be personally excited to see more types of ab initio calculations for this lithium-8 Be2. All right, so just some final conclusions and our future work. These ab initio calculations have helped highlight structural differences between beryllium-7 and lithium-8. We are, of course, doing these calculations to try to help constrain and benchmark these ab initio calculations, but already we're sort of getting a sense that because these calculations were seen to be very interaction dependent in lithium-7 and beryllium-7, there might be something very fundamental, some overwhelming structure occurring in these nuclei that could very well be collective structure. Whereas lithium-8 looks like it's much more sensitive to the details of these interactions, much more sensitive to the choices the interactions make, especially with this LS mixing. These ratios have already been seen to improve what we can do with these ab initio calculations. And I hope to be able to provide further assistance for these calculations moving forward. And there are other nuclei that we can measure at Notre Dame. One potential candidate is boron-12. It is also odd-odd, so it might present additional challenges or similar challenges to lithium-8. And it might also be a little high on the order of things, but I would like to see, we're looking into it. We're seeing what else we can do. So to sort of finish, I'd like to acknowledge all the people who have helped me. All these experiments were performed at Notre Dame, and I'm very grateful to all of the various people at Notre Dame who have done so much work helping me to put these experiments together, get these things going. And of course, to Mark, Patrick, and Anna, our theory collaborators, for all the work they've done. And of course, the funding that's made this possible. And at this point, I'd like to end my talk and open the floor to questions. Thank you.
Thank you very much, Samuel. Very nice presentation. I think the talk, I see somebody already. I think Gregory is up for a question there.
Yes, that's right. Thank you. Sam, thank you for your presentation. Very interesting indeed, and it's nice to see this very nice work on twin cell. A device which is very close to my heart. My question is, clearly you want to reduce the uncertainty, right? Because your comparison to the initial calculations is to some extent limited by your uncertainty. So what are the steps? What is the dominant uncertainty there? Is it statistical or is it systematic? And what can you do to improve it significantly?
Yeah, so that's a great question. The overwhelming uncertainty is absolutely the statistics of in this experiment. That, the lithium-8 experiment, we ended up with a very small Be2 value. So, we sort of made up for our better gamma efficiency with a very small Be2 value. And because of that reason, we had limited statistics. That gives us only so much we can work with, really. Even the sort of second order effects I mentioned earlier, they're going to be on the 10% order, and our statistics are higher than that. So one step that would be nice would be higher beam rate. That's going to be a little difficult in twin cell. The lithium-8 beam is one of our better beams at twin cell, and is like one of the higher rates we can do. So if I want to do a better lithium-8 measurement, probably we would have to go somewhere with a higher intensity beam. That would just be a first sort of step. It would be difficult, I think, to really increase the gamma ray coverage. So I guess it could be done. The beryllium-7 experiment, I think with what we know now, could probably be made more with a lower statistical uncertainty, but we're probably not going to catch the theorists on that one. Their grouping was already pretty tight. So that would be the first step. There are a couple of other sort of steps we could do to reduce the other uncertainties. Like we could get a better handle on our beam, probably by doing some more studies on that, but as of right now, that wouldn't be worth it till the rates are dealt with.
Okay, thank you.
Thank you. While we wait for others to ask, let me ask you a question, Samuel.
Mhm.
So if I understand, there are lifetime measurements of these low-lying states for both lithium-8 and beryllium-7. And as you explained very nicely, that decay is dominated by the M1,
Mhm.
but you excite with the E2. So
Yes.
now you know the E2, you can estimate what correction or what contribution to the lifetime the E2 adds, and then you can derive the B of M1. And so the question is to you and the distinguished theorists, what do they say about the B of M1, which should be also part of the comparison? And particularly, I think in the lithium-8, if you are talking about spin flip, that could be an interesting possibility.
That's a great question. And I think I talked a little bit about determining we have the lifetime gives us the total transition strength. If we have the E2 component, we should be able to find the M1. I talked a little bit about this at a DMP with Libby. So the Abenitio calculations can do the M1 transitions, and because they don't depend as much on the tails of the wave functions, the M1s are a little bit easier to
Yeah,
calculate.
exactly.
Yes. So yes, this is something that could be done. I haven't looked into it. That might be a good thing to follow up at the very least to find, just to find the amount that's M1 versus E2.
Maybe the next paper can be discussed.
Maybe. Well, if I have time on my hands after I have graduated and can keep working on it, yeah.
Thank you. I see another Jack, please.
Hi, thanks for the talk. I was just wondering, for the beryllium-7 normalization, did you look at whether you could measure the decays from the actual decay, the gamma rays from the decay of the beryllium-7 in some sort of beam dump, and use that as a normalization after the experiment?
So beryllium-7 has a pretty long lifetime, so that I think would be doable. It probably would have.
It's about 50 days, I believe.
Yeah, it's in the order of a couple months.
So your candidate statistics should still be pretty good for that versus the 20% or whatever from your yields, right?
Yeah, and the production target we used for producing the beryllium-7 was actually quite hot for a couple of months afterwards. The short answer is no, we didn't look at doing that. I don't. Yeah, it wasn't something we looked into. I don't know if that would have better, if that would give us a better estimate of the beam rate than what we ended up doing. Certainly for this experiment, it didn't end up being our defining uncertainty, but that's a good suggestion from someone I think who's done these measurements before to think about.
Okay, thank you.
Yeah, you cannot. I mean, I don't know. I didn't see, and probably maybe this is sort of compatible with your final error due to statistic. But you can use the goal, isn't it? Can't you use the goal to renormalize to the goal?
Yes. So I tried to do that actually. That was one method I tried to use the gold Coulomb to normalize the beam rate, and quickly found all the fun of states feeding into each other and whatnot.
I see.
Yeah, I'm spoiled by the one excited
That's
state.
one gamma. Very good.
Yeah, it should be doable, but I think because our peaks were so small, it wouldn't have been as good either.
I understand.
Yeah.
Very good. Do I see somebody here? No. Okay. Well, I don't see any more questions or comments? Let me thank you again, Samuel, and wish you all the best with your defending your thesis and the next step in your career.
And thank you for having me here.
There is a lot of virtual ovation. Very good. So I will stop.